experiment that we're going to be doing next week. So the objective of our experiment is to determine the latent heat evaporation of the water using the ground experiment. So throughout the experiment, we'll be using different temperatures and pressures to find the latent heat evaporation. So the equation describes the correlation between the saturation pressure and the temperature, which gives us the latent heat. The equation can be used to determine the changes that can't be measured directly in cases entropy. So the theory behind it is, so you can consider a Carnot cycle, and you can consider any substance that can change phases between T and then T, delta T, and we can consider AB where heat is released, where heat is absorbed between A and B, and heat is released between C and D. So to vaporize that mass, a certain amount of heat has to equal that equation that has to be supplied into the system. The equation for thermodynamicity for Carnot cycle can be shown. So you have work over heat, it gives you dT over T, which we use later. So the change in work is the difference between A and B and CD. So you plug that, so you just, get work, which is pressure over the change in volume, and then the change in work in the Carnot cycle is work between A and B minus the work between C and D, and then expanded, you get this equation. Simplify everything, you get the change in work is equal to the mass times the specific volume of the gas minus the specific volume fluid times the difference in pressure. And you substitute those equations, you substitute equation 1, equation 3, into equation 2, and it gives you this. And then you simplify and rearrange the terms, and it gives you the equation that we're going to use for the lab. So we're also going to apply the use of the ideal gas law. So we're going to assume variation in heat of evaporation is neglected. Vapor phase is assumed to be ideal gas. The specific volume of a liquid is small compared to the vapor. So this is what we're going to assume, and we're going to add into the equation that I showed before. And making those approximations before, the equation becomes this, which is what would be used to approximate, I think I should say specific volume, not specific volume. Yeah. So the experiment is going to consist of a flask with a rubber stop and a hot plate under it. The second thing is going to be a thermocouple. I think it's the same one that we used in the experiment before. We're going to use an analog pressure transducer. We're going to use a mechanical pressure gauge to determine the pressure. An air bleed valve, which I'll cover later why we have that. A vacuum control valve, a centrifugal pump, water reserve, and a computer system equipped with Omega data acquisition capability. So the procedure, as if you read the lab thing that's on Moodle, it's split into 3. Split into like 3 parts. The first part is data acquisition. So when we start the lab, the first thing we have to do is verify the thermocouple and the pressure transducer are connected. Open the program and open the specific file. You make sure the thermocouple and the pressure transducer are configured correctly. Make sure the thermocouple is the correct thermocouple that we'll be using. And next thing you have to do is verify the sample rating for this experiment. So the data will be recorded during the 5 to 15 minutes for the data will be recorded during the first 5 to 15 minutes when the beaker is heating up from 50 degrees Celsius to 100 degrees Celsius. Then we'll verify the data acquisition system records the data for the pressure and temperature correctly. So when you read that, it should be at near ambient conditions. Now, setup and preparation. So you'll be specified whether you'll use heating beads or not. These are used to avoid superheating and allow for smooth boiling of the water. The next thing you'll do is place the glass flask with, fill it up with 2 inches of water, and then place it on a hot plate. And then you place the thermocouple approximately 0.75 inches above the surface. The next thing is to make sure the preserver has efficient water to cover both the inlet and outlet pipes openings from the centrifugal pump. And then you close the vacuum control valve, and then you open the air bleed valve, and then you turn the pump on, and then you open the vacuum control valve and verify water is being drawn in, and then you leak test the system, which is you close the air bleed valve and verify that the stopper in the beaker is drawn firmly and the pressure in the beaker drops. When the pressure is low, which should be about almost 0, you close the vacuum and then you turn the pump off. The beaker pressure should remain low if there isn't any leaks, and then some boiling of the water under vacuum control valve, and verify that the air is being drawn in. Now for the experiment. So you turn on the vacuum pump and bring the flask to the lowest vacuum possible. Leave the vacuum valve control open. Then you plug in the hot plate, and then you set the setting to high. The idea is to bring the water in the flask to a boiling point at near surface pressure. Then you make sure that the thermocouple is submerged in water but not touching the beaker or the boiling beads. And then you begin to log your data after the water starts to boil. And then you slowly close off the line of the vacuum pump and cause the pressure to rise. If done fast, the boiling will stop and you have to restart the experiment again. So periodically check your valves and your thermodynamics. Periodically check valve values, in your thermodynamic table to make sure that your pressure saturated and your temperature saturated data makes sense. So what we do in the experiment should correlate with the data sheet, the thermodynamic tables. So the pressure, before the pressure in the beaker reaches atmospheric, which is 1 atmosphere, open the air bleed valve to avoid any positive pressure buildup. After the water reaches at the atmospheric pressure, stop taking data. Note the pressure and the temperature at this point as a calibration check. So your pressure should be 1 atmosphere. Your temperature should be at the normal boiling point of water, which is 100 degrees Celsius. If the valves are off, then they can be corrected later based upon these observations. And then after that, you just turn off the hot plate and you allow it to be cool. Now, after the experiment, you close the vacuum control valve and open the air bleed valve slowly. Turn off the pump, turn off the heating plate, disconnect the 9-volt power supply, clean up the work area, save your files, and then return to the computer. And you upload your data to a shared document. So your estimated results, so this is going to be a correlation between your pressure and your temperature via the steam tables, which is important because that's how we will know if the experiment is going to be done correctly or not. So once we get our data and once we get into Excel, once we plot the data and all that stuff, it should give you sort of sort of a graph like this. So in order to calculate HFG, so I talked to many people here, and well, I talked to many people who did it, who did the calculations, and the calculations have some errors. So I don't know if these values are correct or not, but what I did is I found a derivative. I took the integral of both the pressure and the temperature to get this, and then, no, you're good. And then I chose a certain pressure, and then certain two pressures, and then certain two temperatures, and then I got the R, the specific R for water, plugged in those variables, and got a HFG, and those are my three calculations. Any questions?